It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on advanced numerical methods and modelling in geotechnical engineering, which will be delivered by Professor Catherine O'Sullivan and Mr. David Wines. Catherine O'Sullivan is a professor in particulate soil mechanics at Imperial College London. Originally from Ireland, she obtained her PhD from the University of California at Berkeley in 2002. Since arriving at Imperial College in 2004, she has continued to develop research that examines soil behavior focusing on the particulate scale. Catherine has authored a textbook on the use of discrete element modeling in geomechanics and has co-authored over 80 contributions to international journals. In 2015 she delivered the Geotechnique lecture. Funding for her postgraduate studies and research has been provided by the Fulbright Program, the O'Reilly Foundation, the IRCSET, the EPSRC, the ICE, the Leverhulme Trust and AGERP. Catherine was a member of the Geotechnique Advisory Panel 2010-12 and is currently a member of the editorial boards of Soils and Foundations, Computers and Geotechnics, Granular Matter, and an editor of the ASCE Journal of Geotechnical and Geoenvironmental Engineering. She served on the BGA Executive Committee from 2009 to 12 and is currently a member of the Committee of the British Dam Society.
Okay. So thank you very much for your kind invitation. I can see from the list of participants that this is probably the most international event I've ever been involved with. So congratulations for bringing together such a community building initiative. It's really, really impressive. So thank you for allowing me to be part of this. So what I'm going to talk about this morning is some of the work that we've been doing that is very fundamental, but that we hope has a practical relevance to dam engineering and also to flood embankments and levees. I'm going to be very mindful of the time, so I'll stop at about 9:45 UK time, even if I haven't got through all my slides, because I think the discussion is very important when we've got such a wide variety of participants. So apologies if I don't get through all the slides, but I will make them available on my website, and you can always ask me questions about them by email. And I should also highlight that really this is a collation of collaborations that I've been involved with over probably the past decade now. And here are some of the key people that have worked with me in this research. I'm going to talk about two design issues in dam engineering that benefit from having a particulate perspective. The first is the idea of base filter compatibility, and the second is the concept of what is called internal instability, or sometimes suffusion. So the issue with base filter compatibility is you have a low permeability core made of a fine grained material. Water is seeping through the core, and if a crack was to develop, you don't want that crack to develop and cause a preferential flow path through the center of your dam. So you have a filter downstream of the core, and the job of that filter is to stop the particles from moving and prevent this crack from propagating into a major breach in the dam. Internal instability is associated with cases where you have a gap-graded material, where you have coarse materials mixed with fines. And you might argue, well, you should never put this kind of material into a dam. But we need to remember that dams rely on being able to source granular materials close to the dam site, especially now when haulage is quite controversial in terms of the environmental impact. So sometimes your materials available to you near your dam site are indeed gap graded. When water seeps through the dam, these small particles which exist in the voids between the coarser particles might be preferentially eroded. This erosion can cause preferential flow so that the erosion can propagate, or it could also in some cases lead to volume loss. So this is quite a significant issue in dam engineering. And just to make sure everyone's on board with this, this is a typical, it's a cartoon of an embankment dam. So we have a reservoir, and the dam is retaining the water in that reservoir, maybe for flood control or maybe for hydroelectric power. In the middle of the dam, we have our low permeability clay core, and that's the bit of the dam that works to retain the water. It's supported by shells, which are also made up of a granular material. And downstream of the core, we see our filter, and then we have a drain, so that the water level downstream is at a much lower elevation than upstream. And I should probably have checked the data on Australia, but in the UK, we've got quite a lot of relatively large dams. And in the UK, we judge the significance of the dam, apologies, by the amount of water it retains. And in the US, there are many, many dams. So this is another diagram of an embankment dam, just really to say there are different configurations. You know, these are really big structures and they tend to have a bespoke design. But in all cases, you will have some kind of a core and some kind of a downstream filter. This is a photograph I took in Greece because we take our master's students to Greece to look at construction there every year. And this is, you know, really a wonderful opportunity I had to see a large embankment dam under construction. There are not so many of these projects in Europe currently. But the reason I wanted to include it in this presentation is you get an idea of the scale of the structures. These are big compaction plant. This is a person. So we're looking at structures that are very, very large, and yet we're thinking in the design about processes that work at the scale of particles that are sub-millimeter in size. It's also important to be aware that a lot of what I'm talking about is also applicable to the design of what are called sometimes dikes or levees in the US or flood embankments in the UK. They also have, you know, some kind of a element. They're earth structures again. There's some kind of an element that acts to retain the water, and they will have filters. I worked a bit on levee design in the US many years ago, and what you see there is those levees were never designed. They're quite different to embankment dams. They tend to be structures that evolved over decades, and the engineering comes into retrofitting them and improving their stability. And there we need to think about filters and the filter design rules that I'm going to talk about in this presentation. Now, there's been a number of guidelines that have been issued for practicing engineers over the past 10 years that consider and provide a more modern perspective on filter design. And these are just some screenshots of them. And if we look at the ICOLD bulletin on internal erosion, we can see that filters have functions they have to retain, they have to be able to be internally stable themselves, and they need to provide good drainage. And in our work, we've been looking at these three aspects of filter performance because they involve thinking about the material at the particle scale perspective. So the empirical rules that are used in filter design to assess whether this filter can retain the base soil look at the particle size distribution of the filter material and also the particle size distribution of the base material. And the empirical rule says that to retain this base material, the D15 of the filter should be smaller than 4 times the D85 of the base. And just in case any of you are not from a geotechnical background, I'll clarify what those terms mean. So in soil mechanics, we quantify the range of particle sizes in a material by looking at a cumulative distribution of the sizes by mass. And D85 means that 85% of the particles are smaller than this diameter, and 15% of the particles are smaller than D15. And typically we use a system of sieves to work out this distribution in experimental work. So what we wanted to do was try to get a more fundamental explanation as to why that design rule might actually make sense by looking at what's going on at the particle size. So here are some cartoons just to illustrate what's going on with retention. We have our base material. You've seen this picture before. And you can see the voids in the filter. But between two voids is a constriction. And for many years, engineers have said that it's these constrictions that determine if a filter works very well. It's the constrictions that trap the fine particles in the core that might want to escape under seepage flow. So what we've done in our research at the particle size is to try to quantify the constriction size and the frequency of constrictions of a given size by using either microcomputed tomography, and these are some images of 3D high-resolution X-rays that have been taken of soil, and also DEM. And what you can see here is in the background some schematic diagrams that have been used over many decades to justify the design criteria, and superimposed on these are some of our images from microCT. And you can see that the real topology of how particles come together is very three-dimensional, and just drawing circles on a piece of paper isn't really going to give you an accurate picture of what's happening in a more complex three-dimensional material. And here are some more pictures. It's hard to capture the three-dimensional perspective here, but you know, these particles are quite a bit behind the front particle, and it's this three-dimensional arrangement of the particles that's developing these narrow points in the microCT, or sorry, in the soil. So we've also, the approach that we took in the research to really develop an understanding of this was to get particle scale data, both using microcomputed tomography, or these high resolution X-rays, but also using discrete element modeling. And then we came up with different ways of deciding where one void ends and another void begins. It's slightly subjective. And then knowing where the voids start and end, we can work out where the void boundaries or where the constrictions are. And then we can get a cumulative distribution, or an idea of the range of constriction sizes in our soil, and compare that to the particle size distribution of that soil itself, or to the particle size distribution of the base material when we're thinking about our filter. So these are some images of the materials we looked at. We looked at materials with a continuous grading, tried to keep things simple, and we looked at different coefficients of uniformity. For microcomputed tomography, we were restricted to looking at quite small samples, and we also wanted to get as high a resolution image as we could. And applying our quality control that we on our data, while we took some images with CUs of up to 6, we felt that our ability to interpret those data with confidence was not there. So our microCT data stops at CU equal to 3. We didn't have these issues with DEM, so we have a broader range of particle size distributions. So just to remind you, we're characterizing our particle size distribution using the coefficient of uniformity, which is the ratio of D60 over D10. I think that's the most common way to describe a particle size distribution in soil mechanics. And you know, we can debate whether it's a good way or not, but it really is the conventional approach. Just to clarify that, I think many of you will be familiar with DEM because of the nature of the presentations today. But the idea in DEM is to take two particles, real soil particles, and idealize them as geometric shapes that we can describe with equations. And the easiest thing to do is to draw an analogy between an individual particle of sand and a sphere. In our DEM model, we allow these spheres to overlap slightly. And at that overlap point, we put in a system of orthogonal springs. The spring that acts in the direction of the contact normal is used to calculate a normal force, and this second spring is used to calculate a shear force. In our shear spring, we allow a force to develop up to a limiting force, which is determined by Coulomb friction. So when this force in the tangential or shear direction gets up to be equal to the product of the coefficient of friction for the surface and the normal force, then we allow sliding to take place. And we can make virtual samples of soil and carry out different tests. And the advantage of this is we can get information in a lot of detail about the forces inside in our material, the particle positions, relative movement of particles, and we can really start to understand the mechanics that underlie the overall complexity of soil behavior. And you know, these are just some key features of DEM. I think I've mentioned most of these, but just maybe to clarify that, I'm going to assume anything I talk about today, the particles are bigger than about 100 microns, so we're not so interested in surface attractive forces. For the simulations we're going to talk about here, we used LAMPS, which is similar to lights. They come from the same code base. And it's a code that can run on a distributed memory high performance computer. So we can have bigger systems than we might be able to access if we were restricted to using a desktop or a Windows software. We have a periodic boundary. So the particles along this boundary see the particles at this boundary, similarly on the top and the bottom. And that means that our tests are free from boundary effects that you would have if you had flat or curved boundary, rigid wall boundaries in your simulation. So when we make a DEM model and we consolidate our samples to a particular stress level by isotropic compression, if we want to characterize the void space, we can use a triangulation approach where we use a form of a Delaunay triangulation to identify tetrahedra in the system formed by particles that are close to each other, and the faces of the tetrahedra define the boundaries between different voids. If you just were to use those tetrahedra that are generated by applying the Delaunay triangulation, you would get an over-segmentation of the void space. So we have an approach to identify when two tetrahedra should be merged to form a single void. For our microCT work, the approach we adopted followed the initial PhD work of Joanna Fonseca, and that was to prepare samples in a triaxial cell and then impregnate them with an epoxy resin. And we used the same epoxy resin that David Frost used in some of the very nice imaging work he did in Georgia Tech back in the 1990s. So we prepare the sample, take it to a particular stress level, and then put this epoxy resin into the sample to glue the particles into place. We then have a sample that is a mixture of soil particles and resin-filled voids, and we want to get high resolution images. If our images have very big voxels relative to the particle size, the particles will look like this, and that's not really an accurate representation of the real particle geometry. In a microcomputed tomography, the resolution, which is roughly the size of the voxels or 3D pixels, is proportional to the size of the sample you scan. So we took our triaxial cell and we extracted a core from the middle of the sample that was about 9 millimeters in diameter. We then take that core to what is called a laboratory microCT system. So here we have an X-ray source. We put our sample on a stage and we have a detector. The source passes through the sample and it's recorded on the detector as a radiograph. And that image is the same as the X-ray image you'd get if you broke your arm and had an X-ray in the hospital. But what then happens is after taking that image, the sample is rotated a small bit, maybe by just 1 degree, and another radiograph is taken. And then the sample is rotated again, and yet another radiograph is taken. And there's a full rotation of the sample, maybe through 360 degrees, maybe through 180 degrees, depending on the setup of the particular microCT apparatus. But you get a stack of X-ray images. And these images can be combined to get a 3D image of the X-ray attenuation of the X-rays as they pass through your sample. So what you see here are two grayscale images, and the grayscale tells you where X-rays are being attenuated relatively highly or relatively lowly. And our eyes can see that that's where the particles and the voids are. So we then need to make the step of automating that so we can do some analysis. So if this is our slice through our microCT image, which is on a grayscale, we need to decide what gray color is associated with particles and what gray level is associated with voids. So we threshold the image, and we have different algorithms for doing that. We then need to be able to separate the particles that appear to be touching, and the algorithm we've used is based on the watershed concept in hydrology that's used to identify what area of a catchment is associated with a particular river. So taking that algorithm, we can have our microCT image, which has at this stage identified which regions of the 3D image are a particle and which regions are void. We can apply our watershed segmentation, and we can use it to identify individual voids. Once we know those voids, we know where our boundaries are, and we can get a map along a constriction of the distance from every point to the nearest particle, and the local maxima we take as being our constrictions. And we've taken a DEM sample and converted it into the same data set we used in our microCT analyses, and found that we got broadly similar results for the two approaches. We wouldn't expect them to be exactly the same because there's a degree of ambiguity in what is a void. The void space is continuous, and how you partition it is never going to be completely objective. But one thing we've done is to run some simulations of flow through our microCT images using computational fluid dynamics. So we take our microCT image and make the surfaces of the soil grains to be the boundaries to the fluid flow. And that gives us detailed information about the velocities and pressure gradient in the sample. We use some comparisons with permeameter tests to make sure the results were reasonable. But we can then see that the constrictions that we associate by considering the geometry of the void space alone, they do correspond with the local maxima in the velocity of the fluid of the flow. This is assuming laminar flow. And so we're reasonably confident that our partition method is relevant to thinking about the movement of water through soil. So then we have our particle size distributions that we considered in microCT, our particle size distributions that we considered in DEM. And we have an ability to go from looking at these particle size distributions of what we can consider to be modeled filters to a constriction size distribution. And these are data for the DEM sample. So we have our range of particle size distributions in the filter, normalized by the smallest diameter. And here are the range of constriction sizes in our sample, again, normalized by the smallest diameter in the filter. And we see that our constrictions continue to increase in size as CU goes from 1.2 up to 3, and then they don't seem to get any bigger. So we've got very similar constriction sizes for CU bigger than 3. And we see for the lab data, again, we see that as our CU increases, we can see an increase in the constriction sizes, but we can't say anything about CUs beyond 3 for this data set. But we are getting similar results where the CUs overlap between our microCT and our DEM analysis. And then we looked at this idea of D15 of the filter being of importance, because in the end, this is all very interesting mathematically, but we want to say something that's relevant to engineering design. And this D15 of the filter has been picked up since the time of Terzaghi as being a diameter we should be thinking about in filter design. And we see that if we normalize by the D15 of the filter rather than by the D0 of the filter, that normalization gives a narrower ranges in our constriction sizes. So we can say that the D15 of the filter is a characteristic diameter that for samples with continuous grading is approximately telling us something about the distribution of sizes of the constrictions in the filter. And we see the same thing with the microCT. When we normalize by D15, we unify the data better than just normalizing by the smallest diameter of the particle in the system. There is this idea of a controlling constriction size that Kenny defined. Kenny did some very good work on filters from a soil mechanics perspective in Canada in the 1980s. And he did a lot of experiments where he looked at how much of a base material with a given particle size distribution would move through a filter. And he said the largest particle of this base material that gets through must be close to the constriction size that controls the passage of material through the filter. And Kenny looked at how this controlling constriction size varied with CU, and you can see that as CU increases, that controlling constriction size increases, and there's a subsequent decrease. And our DEM simulations, when we looked at our median constriction diameter divided by D15 of the filter, we saw a similar trend. So that gives confidence that our DEM analysis and our interpretation of the data generated do relate to physical systems. And we also looked at the density of constrictions or spacing of constrictions in a filter. And this is important because you want to know how thick your filter should be in order to effectively retain the base material. And we found that if we looked at our constriction spacing divided by the median particle diameter, for our more or less continuous gratings, there was a relationship between this normalized spacing and the coefficient of uniformity. And when we compared these data where we could directly measure constriction spacing, either using microCT or DEM, to the literature, we found that some of the empirical correlations that have been proposed in the literature grossly overestimate the constriction spacing at low CUs, grossly underestimate the constriction spacing at low CUs. And it's only the empirical formula that look at the distribution of particle sizes by surface area that give a good estimate to our direct measurements. So what we want to then know is, what about this ratio that they've been using in filter design, this D15 of the filter to D85 of the base. So, you know, you can plot the particles size distribution of your base material, and now we can plot a constriction size distribution for your filter, and you can look at the two of these till you're blue in the face, and you can't really say a lot that's sensible. We spent a long time trying to think, how do we say something about whether or not this base material will be retained by a system of constrictions with this distribution? And we realized that the best way forward was to do some kind of a network model analysis. When Adnan Sufyan was working with me at Imperial, we did something that's much more sophisticated, that's in the process of being written up at the moment. But this is the first attempt we made at this, in which we just assumed that we had a regular lattice, and this came from Tom Shire's PhD. So we weren't concerned about the topology of the lattice. And we said, well, this is an idealized system, and we're going to say that the nodes in this lattice represent our voids, and the edges that connect these nodes are our constrictions or our pore throats. And obviously the way these would be connected in a real material is more complex, but let's just accept that the design guides don't care about the fabric of the void space. They just want to know about the size of the openings. And let's use this very simple model to say, if we isolate and only consider size, are we able to see something sensible? And the way the model works is it's a random walk model, and we have are individual nodes, and particles can come into each void through 3 entry edges, or they can leave through one of 3 exit edges. And the likelihood of picking up one of the edges depends on the area of the constriction assigned to that edge. So we have a distribution of constriction sizes that in this case we got from a DEM simulation. We assign those to all the edges in the system, and then once a particle gets into a void, whether it's going to choose any one of these 3 edges to move with depends on the area of that edge. When it tries to move, it's either going to move through because the particle is smaller than the edge, it's going to be retained because it's bigger than the edge, and then that edge becomes blocked, and eventually it might be retained in the void if all the edges are blocked. And then if we look at the largest particle eroded versus the median diameter of the base, we could look at how it varied with the ratio of D50 of the base and D0 of the filter, and we can see there's a variation. But in general, we're going around this controlling constriction diameter that Kenny found for a CU of 6 back in his experimental work. And we're then able to look at some of the guidelines and filter design that were actually developed in Australia by Robin Fell, and looking at ideas about no erosion and continuing erosion that might occur depending on your base material and your filter material. And what we can see is that if your D15 or the filter divided by the D85 of the base is less than 4, you're going to get very, very little material eroded. And then as this increases, you start to get progressively more and more erosion. So we were then able to look, and I haven't gone into details in the presentation, at some of these empirical studies that have provided a lot of insight and come at them from another perspective and confirm that. So the next thing I'm going to talk about, and I'm mindful that I don't have a lot of time, is diffusion, and that's the selective erosion of fine particles from the matrix of coarse particles under the action of a hydraulic gradient. And these are some cartoons that were developed by Paul Slangen and Jonathan Fannin that I've redrawn here. And you could have a scenario, as I've already said, where you just get movement of particles and an increase in permeability, or you might in some cases get a change in volume that would lead to settlement. So some key work on this was done by Skempton and Brogan working at Imperial in the 1990s. They did gap graded material. They put it into a rigid wall permeameter, and they had water flowing up through the material. And they plotted the discharge velocity, or the flow per unit area, against hydraulic gradient. Now, if this material was to obey Darcy's law, we'd expect this to be linear. But at a hydraulic gradient of 0.1, we start to see a deviation. And this doesn't mean that Darcy's law is incorrect. They haven't done anything as dramatic as that. But what's happening is that these very small hydraulic gradients, the finer particles are starting to move, and your permeability is changing. And we're seeing complete failure at a hydraulic gradient of 0.3. And this is a photograph taken by one of my MSc students a few years ago. And you can see this region of the soil where the fines have been completely washed out up to the top through the side of the rigid wall permeameter. And many, many years ago, when I lived in the US, I worked for Woodward Clyde, URS Griner, and we were looking at how can we improve the safety of the levees that go through downtown Sacramento along the side of the American River. And my job as a graduate engineer was to work out, if we put a cutoff wall through the levee, could we reduce the occurrence of piping on the downstream side of the levee? Because there'd been a number of winters where they'd seen incidents of piping, and they were very worried that if these piping incidents were to develop, the levee could be undermined. And my design criterion there was a hydraulic gradient of 1. So we were trying to make sure that we got that we said if failure happened, it would happen when there was a hydraulic gradient of 1. But here, Skempton saw failure happening at a much lower hydraulic gradient. So this is a really, really significant thing to be aware of if you're involved in design, because it could change the way you apply your design criteria depending on the material you're looking at. And we know that this phenomena of preferential erosion of fines almost led to the collapse of Bennett Dam, which at the time of construction in the 60s was the largest embankment dam in North America. And this is a diagram of the Bennett Dam, and here is the particle size distribution of the transition material in zone 2, and you can see it's a gap graded material. And in the 1990s, they discovered a big sinkhole on Bennett Dam that was caused by preferential erosion of these finer particles. So a lot of thinking has gone into this, and this conceptual diagram is very useful, and it shows that this phenomenon of internal erosion depends on the geometry of the material. That's the particle size distribution and the size of the constrictions in the void space, the stress state, and the hydraulics. And in various bits of research, we've been able to look at this. The first thing to think about is the geometry. So what they do with the filter criteria is they apply a filter design rule that's very similar to what we look at when we consider base filter compatibility. But now our fine material is not in a separate layer. It's the finer grains that are in your gap graded material. And D15 is not a D15 of a filter that acts on its own. It's the D15 of the coarser fraction of your material. So we use microCT, and we looked at different materials, a material with a continuous grading and 2 gap graded materials. And we applied the empirical criteria, looking at this ratio of D15 of the coarse material and D85 of the fine. And we can see images of how the coarser and finer particles are related to each other. And we can see qualitatively that as this ratio increases, and our empirical criteria says that it becomes more susceptible to internal erosion, we can see that the fines are less constrained by the coarser grains. They would be freer to move if there was a seepage flow applied. And with our microCT data, we can start to make some quantitative measurements of the microstructure. So we looked at the coordination number, which is the number of contacts per particle, because that's an indication of the kinematic constraint. If you've got contacts all around a grain, it can't move that easily, but if it's not constrained by other contacts, it's free to move. And we could see that there was a definite correlation between the coordination number and this Kézdi ratio. And we looked at this also with DEM, and so there was an offset, which we can explain by the difference in geometry between our angular sand particles we scanned in the microCT and the spherical particles we used in DEM. And then in Tom Shire's work, we looked at Skempton's explanation for the preferential erosion. And Skempton said that the fines carry less stress than the coarse grains, because the coarse grains effectively, the load preferentially is transmitted through them, and the hydraulic gradient where you start to see migration is related to the proportion of stress carried by the fines. So based on his permeameter tests and looking at these data, Skempton estimated that the stress in the fines was about 0.2, because that's when he started to see strong piping of the fines. And we revisited this idea by carrying out DEM simulations of gap graded materials. So that's materials where we have a mixture of coarse and finer grains with different fines contents and different size ratios of the coarse and finer particles. And we could look at what Skempton was inferring from the hydraulic gradient, which is the average stress in the fine grains divided by the applied stress. And we found that we got a similar answer to his alpha when we used the same particle size distribution as he had considered when we looked at a loose sample. And his sample and his experiment would have been loose. And that gives us confidence that our results are sensible. And this is an image of all the different particle size distributions we looked at. And what we could see is that the proportion of stress in the fines depends on the fines content. So if we've got a fines content of less than 25%, the fines carry relatively low stress. If it's higher, they carry a relatively large amount of stress if it's higher than 35%. And there's a zone where the proportion of stress carried by the fines depends on the density. If there's a systematic increase in the stress carried by the fines as the sample density increases. And this diagram confirms hypotheses that Skempton and Grogan put forward. They described that if you have less than 25% fines, your material is underfilled. And if it's greater than 35%, it's overfilled. And they made this recommendation just kind of looking at samples. They could never really see into the interior. But what we've done is said that, yes, their hypothesis on which their paper is based, it is borne out when now we can go back in and make these detailed measurements. So I was going to talk a bit about coupled simulations, but I'll leave that and leave time for discussion and just say that there is scope to couple DM with computational fluid dynamics and simulate particle migration. But as we've got to 9:45, I'll just go to my conclusion slide and take some questions.
So we have one question so far, and this comes from Ahmad from Iran. Ahmad asks, what code do you use for DEM simulations?
For the data I've shown there, we used LAMPS. But we've also done a lot of work with PFC, including coupled simulations with PFC. And one of the people working with me at the moment is using Yade. So we are mixing and matching codes a bit. And the initial work I did was all with Truebill.
Yeah, so we have the second question comes from Ramesh from IIT Madras. And he has a couple of questions. So basically Ramesh wants to know if permeability in this porous material is a transient process and how to quantify that. Why CSD is with number and not volume?
So first of all, permeability is transient. Permeability will evolve if you have erosion. So in terms of the change with time, you would have to take scans at different times and then look at your, you know, if you're trying to relate it to the constriction sizes, which you could do through the Kézdi-Kármán equation, you would have to just take different snapshots. In terms of spatial variation, that's a very good point. Permeability is highly heterogeneous. So even within, and I could show some, go back, and you can see that, you know, the voids are very different. And, you know, that, I think that in Howard's data, you can see that it really does change. And you've just got to go into the, this idea of a representative element volume, you know, that you have if you're looking at contact forces or anything at the particle scale. I mean, this is the image I wanted to show. So you can see here that there's a very big variation in velocity, even in this very simple material. So it's very heterogeneous. But if you're trying to say something, you just need to make sure that the sample size you're looking at is representative. And I think the other question, I think there was another question there about why do you look at your constriction size distribution by number? Well, constrictions don't have a volume. We spent a bit of time looking at that, and we had thought, well, you could look at your constriction size distribution by area. That could also be valid. But in the end, we couldn't really see a justification for that. But they definitely don't have a volume because they're just a denotation of where one spatial region begins and another spatial region starts.
Okay, thanks. This question comes from Alex. He wants to ask that which one of the following do you consider most suitable for the failure of a salt suffusion? Is it production of fine, settlement, or maybe change in hydraulic conductivity?
I think it's difficult for me to say, but I would have imagined that the key issue really, settlement is less of a risk than collapse. So the key thing you're worried about is collapse. And if you start to get a lot of preferential erosion of fines, you'll get a big increase in permeability. That will attract flow to that area. So the seepage flow velocity will be higher there. And then you'll start to get erosion, not just of the finer particles, but also of the coarser particles. And you could, you're just getting the material being completely eroded away, and that could lead to a collapse. And when you look at that image of Bennett Dam, where you see that there's a big hole in the dam, you can see that that's what happened there.
Thanks, Catherine. This one comes from Benedicta from University of Edinburgh, and mentions that she had used resin to impregnate rammed earth before. Is it possible to explain more in detail about how do you impregnate the resin when the specimen is in the triaxial cell?
Yeah, to impregnate rammed earth could be quite tricky because the permeability will be a lot lower. What I would, we impregnated it very, very slowly and checked the permeability of the material. We followed, as I've already said, the procedures that had been already developed in Georgia Tech by David Frost's group. But we've never looked at low permeability materials such as rammed earth with this.
Okay, let's take the next one. This question comes from Professor B. Amir from Jammu and Kashmir, India. And he mentioned that particle size distribution is indeed a critical property when we look at dams. And what would you consider as an appropriate methodology for determination of PSD of dam granular material?
You can use sieving, it's quite cheap. You can also use, we have a laser system in our lab that was developed for quantifying particle morphology for chemical engineering practices. That's very easy to use and very fast. The problem is the capital cost of getting something like that. It cost about £50,000. So maybe on a dam site, that might be cost effective to have one of those. I don't know. It really would depend on how many, you'd have to look at the labor costs of sieving versus the capital cost on that equipment. But there are alternatives. It's just you have to weigh up the economics of it.
Okay, let's take the next question. Let's take this one. This first comes from Mehrdad from University of Melbourne, and he asks, how could you relate the local maxima in microCT images to the voids inside the sample?
So the local maxima, so if we go through that again, it's quite hard to get your head around it. So we've identified what are the voids. Then we see where, probably here you can see this void meets, this orange void meets this blue void along this point here. So that is probably this, I can't pick out, it's probably this blue cluster here. So that we say is where those two void meets, that's a void boundary. And then we take the cloud of dots that define that void boundary, and then we measure the distance between each point in that cloud to the closest particle, okay? So what you see here are a cloud of points or a cloud of voxels that represent the boundary between two voids, and they're colored by the distance of each voxel to the nearest particle. And when we get into the middle, we see that there's points that are further away from particles than any other points on this boundary. And we would imagine that they're the constrictions. They're the points where you're going to see a local maximum in your velocity, because the velocity streamlines are pushed close together. So that's what we meant by the local maxima. And this is published in Computers and Geotechnics, and the first author is Taylor.
Thanks, Catherine. Let's take this question. This looks interesting. So this comes from Omar from Iraq, and he says that if it is possible to apply suction during CFD DEM coupling to represent the behavior of unsaturated sand.
that would be really difficult. We find it hard enough to deal with saturated simulations, but I think in computational fluid dynamics, they can deal with two-phase flow. So maybe you could do this, but it would be quite tricky.
Okay, let's take this one. This one comes from Andrea from Politecnico di Torino. And he has a question about the procedure. If it is an expensive procedure, how many times does it require to be carried on?
We don't have a microCT machine. They're incredibly expensive. I'd love to have one, but we don't. But that hasn't stopped us doing the research, because you can pay to get the scans done. Universities that have microCT typically are open to other people using their facilities for a fee, and then they can use that money to maintain the equipment. So we've done some scans, very early scans we did in materials at Imperial, but then we did scans in Nottingham. They've got quite a good setup for commercial testing. I think anyone in Europe could probably use it. You can just Google them and send them stuff in the post. And then for Howard Taylor's work, we had an arrangement with Queen Mary University where we were paying to use the machine, but they also trained him up. So it was a bit cheaper. So they didn't have to have a technician, but they felt he was competent in doing it himself. So if you want to get going with microCT, you can just Google, what universities have the facility, and you can either go there or you can send the samples by a courier or in the post. Which is what we did. So I think if you've got, a couple of €1,000, you can probably get a scan done. The number of scans you need to do, that depends on the material and what you're interested in.
Okay, the next one comes from Yang from Huahai University, China. And his question is that, how do you consider the particle breakages of filter materials?
We didn't in this, but I mean, there are different ways you can consider particle breakage if you're looking at a DEM model, but in these studies, we didn't look at breakage. But it would be doable. You just have to have a criteria for breakage and then repartition the void space.
The next one comes from Reza, who is a PhD candidate at University of Melbourne. And he asks, could you please explain the effects a particle save in your DUM simulation regarding the force distribution and coordination numbers? And if spherical particles are enough representative of the real specimen? It
depends on whether spherical particles are sufficient, depends on what you're looking at. There's a lot of data out there to show that DEM simulations on spheres can capture key aspects of granular material behavior, and you can use them. The advantage of spheres is you can get quite a lot of spheres into your sample. And for some particle size distributions, getting a number of particles in is very, very important. If you've got particles that are angular and bumpy, you will have more contacts per particle than you would if they're perfectly smooth, because if you look at my knuckles, I can interact my knuckles at 4 points because they're rough, whereas if I take these 2 cylinders on my desk, they can only interact at 1 point. And that increased coordination number brings in resistance to rotation between the particles, and that increases strength. And whether you need to do that depends on the particular question you're asking.
Okay, this one comes from William from Valley, and he asked that if the infiltration of water into the soil particle, isn't it a mechanism for scour?
The scour would be a surface erosion. So that would have a slightly different mechanism because the flowing water picks up the particles from the surface. And I don't quite understand the question about the water getting into the particles, but we are dealing with relatively low pressures here, so we're not at a sufficient pressure that we would break the particles.
Okay, let's take the last question for today, and I think then we can close the first session. This one comes from Carlos, who says that if you have found, depending upon the sample's density, any metastable structures which produce a collapsible behavior on triaxial states.
Yes. So normally when I presume this is for DEM, normally when we're creating very loose samples, we use a high coefficient of friction. And sometimes we make a sample and we isotropically consolidate it, and the minute we start to try to pass a shear wave velocity through it, or to shear it in a simulation of a traxial compression test, it collapses. So I don't have like a formula, but for certain particle size distributions, that certainly happens, because we've been doing a lot of work on relating stiffness to the particle scale parameters, and we've made these samples, and then we just run a stress wave through them, very low amplitude, and the whole thing collapses, and it's very frustrating. So we're trying to avoid that happening, but it does.